Let's talk about difference equations. In a lot of different fields, you want to model a dynamic system. So this is something that changes over time, has different states, and you want to model it mathematically so that you can make predictions. Features are measured at discrete time intervals, and you're going to collect this data into some vector, say x0, x1, x2, and so on, where the entries of the vector represent some information about the state of the system at that given time. If, in this setup, there's a matrix A that has the property that the state vector x1 is A times x0, x2 is A times x1, and so on, so that xk plus 1 is A times xk for k equals 0, 1, 2, and so on, then we say this is a linear difference equation, or a recurrence relation. And this is the setup that we can analyze using linear algebra. So here's an example from page 84. Suppose we just have a simple population migration model. So we're going to measure yearly movement between a city and a suburb, measuring time in years. And so suppose time 0 is the year 2000. Okay, so suppose we collect a bunch of data and we notice that overall, over the course of a year, 95% of the people in the city stay in the city, and 97% of the people that are in the suburbs stay in the suburbs. What that means is yearly, there's a migration of 5% of the city population to the suburbs, and a 3% population migration from the suburbs to the city. And so we're going to measure the system. So we'll let CK be the city population in year K, and SK will be the suburb population in year K. We're going to put this together in some XK state vector, CK, SK. And now we're going to try to analyze what happens 1 year in the future. So CK plus 1, that's the state of the city population in year K plus 1. Well, 95% of the city population stays put, so that's the 0.95 times CK, plus 3% of the suburb population migrates into the city and contributes to that population, so that's 0.03 times SK. The suburb population at time K plus 1, well, there's 5% migration from the city to the suburbs, so that's 0.05 CK, plus 97% of the suburb population stays put, so that's plus 0.97 SK, which means the state vector xk plus 1, which is ck plus 1, sk plus 1, can be represented as this matrix 0.95, 0.03, 0.05, 0.97 times the state vector ck, sk. And so this is called a migration matrix. This matrix 0.95, 0.03, 0.05, 0.97. And so we have that the state vector xk is equal to this migration matrix M times the state vector at time k. All right, so let's see what we can do with this. Suppose in the year 2000, the population is 600,000 in the city, 400,000 in the suburbs. What's the population in 2002? Well, so we're given that x0 is 600,000, 400,000. If I want the population in 2001, which is I can analyze using the vector x1, I multiply m by this x0 vector, and I get 582,000, 418,000. If I want the population in year 2002, like we're asked, then I need to compute x2, and so I multiply by this migration matrix A, and get 565,440, 434,560. And so the components of that state vector are the city population and the suburb population. So what is this useful for? Well, one of the things this would be useful for is to try to study the long-term behavior, right? So we have this very simplified model where we're assuming certain migration patterns, But if you were a city planner or trying to plan, public transportation or something, you might want to know what's going to happen in the future, right? What's the long-term behavior of these populations? Do we need to plan for many, many more people in the city, or better infrastructure in the suburbs? What's the long-term behavior of this system? So this is essentially asking what happens to the state vector xk as k goes to infinity. And the answer, unfortunately, is not in this section yet. We have to develop a little more theory first, but we'll be able to answer these types of questions in terms of eigenvectors and eigenvalues, and that's in chapter 5.